Hey everybody, welcome back. All is well, I hope. Okay, we have had the quiz in your timeline, at least. We've got a lecture here. I've been looking at sort of how we're doing. I've made a judgment call, and that is that we're just kind of overall ahead of where I need to be. I think it's just we have no holidays that interrupt us this semester. I've given the same course in semesters where there's 2 holidays that interrupt and take these huge chunks out of my lecture time. So this is the day before the Canada Day holiday. So at least with respect to this course, we'll call that a 2-day, like a midweek weekend. Why not? Yeah, I'm ahead of the exercise schedule, which is for me the real schedule for the course. I know we have lectures. The lectures are in service of the exercises. So we were, well, classifying stuff. You know what? Maybe my notebook is the better. This is a Jupyter note. It's the new Jupyter notebook I had last week. I've updated a little bit just for the demos I want to do today, but I've created this 4-dimensional data set, or data set with 4 features, I guess I should say. And then the thing that I'm trying to predict, which is what category is it in? And this looks hard, right? Now, it's 4-dimensional, which I have plotted in 2-dimensional scatter plots. So, you know, like category purple and category green, those seem easy. Category red, orange, and blue. Red, orange, and blue. Well, okay. Like I can see, like over here, red and blue are kind of far apart. Orange is smushed into them both on, you know, in all 4 dimensions, it looks like. So, you know, I would hope to get some results here. You know, often in machine learning problems, I have more dimensions than I can visualize. It happens that here I have 4 and I can kind of cobble my way through to a couple scatter plots. And what we're doing here is we're creating the collection of features, the inputs, the things we measure or know or observe or whatever, and then the target, the thing we're actually trying to predict. It's categorical, so I'd better choose a classifier. Good job, I did. Break the data into training data that we'll use to train the model, and validation data that we will use to evaluate. Well, validate, I suppose. This is where we were last week. This Gaussian naive Bayes that assumes independent features normally distributed for each category and feature pair. And we got pretty good scores. Like looking at this, like I'm surprised, right? Well, maybe I want more data. I already increased this actually since last week. Well, why not? Like if data points are this cheap, why not have a lot of them? Usually you don't get this luxury, right? Usually you have to deal with the data you got. So lots more data. Does that make it better? Nah, but we'll call it probably the same. I don't think that's doing anything. Okay, and we had done this. I'd shown this classification report where we can see things like, you know, which categories are we bad at? So category 3, wait, can I label them? Target names, you can. I had done this. Sorry, I in my next demo here, I've got this. I went through the bother of actually figuring out which one was which. Boop, boop, boop. Category 0 is purple and blue and green. So what was I just saying? I think I said orange looked harder. And yeah, the score for orange things in category orange is lower. I guess that's probably what I'd expect. It makes sense. Again, I'm also doing not super hot in category blue. Oh yeah, category blue is also like, well, it's probably confusion between those two. Oh, funny, I just used the word confusion. I had that from last week. The thing I've added in here is this confusion matrix, which is it's a visualization of well, I guess what category got confused for what. Like what I'd really hope for here is like a perfect diagonal line. So I'm seeing here that, when something was orange, a few times I confuse it for category blue, once for category purple. So this is on, with this model and this validation data, it does the things, it checks, where is the true, where does the truth and the prediction diverge? Well, I guess it checks everything and compares for you. I don't know, did I learn anything? Like probably on this fake data, no, I didn't learn anything because it's fake data, but hey. And I think that's sort of back to where we were. Let's do another thing. So the naive Bayes is fine. It's, well, I don't know if it's simple enough. Like we make all these assumptions about probability, and we're kind of assuming, just so we can assume something about the distributions, that we have normal distributions and independent. Maybe we can do even better. So let's try this. What about just what training point are we closest to? So I have this data on the slide that's got two features, got plotted as X and Y. So this is with the training points, right? So the background that's being drawn is what color is the closest training point. Okay, like this is, almost telltale overfitting, right? There's all this stuff going on that's probably not real. And because, yeah, like, there's one red training point over here. So that creates a little red polygon there that in that area will predict red because that was the closest training point. And then if I put the validation data on that same model, right? So the model's the same on either slide, just the data that's overlaid on top of the predictions. Yeah, right. It seems crazy to predict category red over here. There's a whole lot of green points around that, but there is one red point, so it wins for its little neighborhood. Well, there's an S there. Maybe we can fix it. So what I just described was, well, look for the one nearest training point. Fine. But maybe I can have more than one. Look at a couple. And just effectively vote. Look at the 5 closest training points in my example here, and then take the most common category of those 5. You might have a tie in some way to break the tie, but we hope for not too many. And off we go. Okay, so now this seems like it's overfitting much less, right? The decision boundaries are kind of reasonable. I bet if I look at the score and the training data and the validation data, it comes together a little bit. Maybe this is a pretty good model. And yeah, like that's what I see here. And this is simple. Like this is the thing you could describe to your like little cousin or whatever, right? It's like, well, how will we decide? Well, we'll look for the examples that are most similar. Like it's almost like even phrasing this as machine learning feels a little bit, optimistic. It's not. It is like we are learning from the data, but all we're doing is saying like, what does it look like? It looks like the red ones. Okay, it's probably red then. And that's all there is to it. We've got this little trade-off. Like we now have a choice. We have a hyperparameter to choose, which is the K. How many neighbors are we going to look at? And as always with these things, if it was obvious and simple, it wouldn't be a parameter we have to fill in. So we have to make a choice. If K is small, we're going to, chase around individual training points. If K is too large, we need, if I chose K equals 100, well, I need, I'm looking at 100 training points. That means like I need at least, sort of 50 training points or whatever to do anything in my model. Maybe I don't have that many training points. It depends on my data set. So let's try it. Let's try it with this data. So same data, and I'm just going to swap out that. I did the import, and the scores are almost exactly the same, and the outcome is almost exactly the same because my like really simple fake data here is just a little bit too simple. What if I roll the dice again? if I just have a different random seed, oh, see, I think that's probably easier. Yeah, like random is being random. It'll come and get you. Yeah, like I just randomly have a simpler thing here. But hey, I don't think I'm overfitting. I'm gonna go back. I like the worse is better. So let's have a look. Let's have a look at that. Like I said, a small k probably means you're going to overfit. Let's do that. If we say k equals 1, okay, so certainly if I say k equals 1, it should be no surprise that I do perfectly on the training data, because what else would it be? If I look, what am I going to predict for this training point? Well, itself, because it is the closest point to itself. Yeah, that seems predictable. And yeah, I do a little worse on the validation data, which is a sign that I'm overfitting. What do I see? Well, again, I don't think this is going to be very interesting for this data. There's just, again, the fakeness of it is what it is. And then as I start dialing this up, I think I have 1,000 data points here. So maybe I can get away with 100, right? And I get a good, ooh, that's better, isn't it? So wait, before I was at 5, and I'm at like 91. Let's look at that one. So like, ooh, actually gets a little better. Training score similar. Maybe that's just an accident. So in this data, everything being what it is, I have enough to support k equals 100. Yeah, at some point, I was looking at, at some point, am I just looking at all the data? Anyway, let's not push too far and teach us some crazy lesson there. So easy, right? I now have a little work to do as a programmer, expert, data scientist, whatever I am in my story. Okay, I'll play around a little bit. I'll try to increase my k so the model has more to look at, but then because I don't want to overfit, but then I don't want to underfit, so I have to find somewhere in the middle, and it depends on the problem in the data set. So these two, these were the things that Gaussian naive Bayes failed at because, well, we didn't meet the assumptions. So yeah, that's probably reasonably predictable. But I get that. And this seems cool, right? Like that's a pretty good decision boundary that I feel like I'm happy with. It's a little noisy. I played around a little bit. I didn't pour my heart and soul into this, but K of 9 seemed to work pretty well in these data sets, and more and less was not better. Like there's a pretty big plateau here of these are pretty easy. I get 100% on this 2 interlocking arcs data set because yeah, you would, right? Yeah, what's near here? Blue points. What's near the red points? Red points. And there's no hard overlapping stuff. But when it gets down to it, all of this stuff, like 2D points, okay, I have 4-dimensional points in my notebook over there. They're just fake data, right? I'm not apologizing for it. It is what it is. My real data, I'm putting on assignments, so you can play with it there. But there's all of these other things, and there's a few of these, and they all work today. That's wild. Usually at least one of these is down. These are like the iris data. Boy, it's like it's a law that if you're going to publish any kind of machine learning tutorial, you have to use this data set. Either this or handwritten recognition. Those are the 2 things that every machine learning tutorial does. And this is just it's some flowers, right? So it's 3 subspecies or varietal or whatever they are of this flower, and a couple measurements on each flower, the width and height or length and width or whatever it is for a couple of things. Can you tell me what type of flower it is? And the answer is yeah, actually, it's pretty good. It's a pretty easy problem, but it's therefore a good machine learning problem, right? I don't obviously know, at least as a non-plant person, how to decide between these things, but I can use machine learning to classify them for me and do pretty well, and that's great. So there's a lot of these data sets out there. One thing I will warn you about, as like if you are looking towards the project in this course, that of course you don't really need to be yet, but it's time to maybe start thinking about it. Like as we're coming to the end of machine learning, it's time to think about the project. So we're not quite there yet, but we're getting there. These data sets are boring in the sense that like they're there for one thing, right? Like what do I, you know, it's data that's designed for exactly that task, and I can do that task on that data. That's a perfectly fine machine learning tutorial problem. It's a crap project because there's just not enough to do there. These data sets are clean and beautiful, and they have exactly the data that you, or the features you need to do this one problem. Again, good demo, yawn of a project. But anyway, there's a lot of stuff. Again, I'm just using these fake points in lecture, but there's a lot of other much more interesting things out there. I'm going to look at this. In fact, it was on the screen there in the UCI. This breast cancer data set that's also, again, it's out there. It's super common. It's exactly the same 569 data points that are in everywhere you see breast cancer data set in a machine learning context. It's this exact data set. But the question is, well, they measured 30 things about each person, 569 of them. Each one of those like observations, suspicious molds or whatever they were, suspicious growths, either was cancer or not. And to give you an idea, I don't know which ones. I've always assumed that 1 means yes cancer and 0 means no cancer, but I don't. I probably says here somewhere. So what do we do with this? Right, this is very different, and I have it over here. Like scikit, again, if you want to know like how common is this data, like scikit-learn just has these like magical data set loaders that will just find you the data and download it from wherever. So what I've done here is pandas data frame it, just so you can have a bit of a look. So it comes with just a matrix of all their things and then a separate array of feature names, which very convenient column headers. Okay, so what do you do about like, if we're talking about a breast cancer or possibly breast cancer growth and the mean compactness is 0.2776, I don't know, like, am I happy or sad about that? No idea. But maybe we can figure it out. And then what I should include here as well is, well, there's the thing we're trying to predict, right? So, whoops, pardon me, I'm in the way. Again, is let's say 0 means not cancer. So, is there something about all of these numbers that we can put together, use some kind of machine learning tool, and kind of reliably come out with the right category? I know it looks like there's only a single one in there. That's not true. It's reasonably balanced. So, well, if we just like go for it, right? So I'm just Gaussian naive Bayes, whatever. Maybe these are normal distributed. I don't know. I mean, I could look, right? I could spend some time on that, and I could have a look, and I could say, well, if I do a yeah, again, mean compactness. Why not? Probably not very normally distributed, right? Like I might expect, well, it's not wild, right? It's, if I was doing a stats test on this, I would think maybe I don't want to do a t-test on this data. This is maybe not normally distributed, but hey, maybe it's close enough. Maybe it's close enough that whatever I'm doing with Gaussian naive Bayes will get me a decent result. And hey, look at that, 94%. and maybe this is just a moment of professional ethics. um, this number is a high number. I am happy, but like, what does that mean, right? Like, 5.5% of people who have cancer, we're going to send home and say, you're fine, don't worry. And half of the people who don't have cancer are going to be scheduled for an operation. Like, this is now something I'm very suspicious about. This, it's a small percent, but I'm not happy with that. But we'll move on. Again, if you're making any kind of cancer diagnosis based on anything you do in this course, you deserve to be like sued. But hey, I got a pretty good score, right? And that's not, again, ignoring the medical reality of it. I think that's a little bit of a surprise, right? That I can just like wave the Gaussian naive Bayes magic wand over this data and kind of sort some stuff out on it and get somewhere at least. That's cool. My k-nearest neighbors is a little bit worse. So it was at 94 down to 92. All right. So I guess, k-nearest neighbors does a little bit worse here. I don't know why. Well, I do and I don't. Because these aren't just now fake data points. Like, these are numbers that actually measure something. And I don't know what worst concavity measures. I don't know what the unit is. I can guess the unit of mean radius is a length, even if I don't know if it's like millimeters or whatever. But these are pretty different values, right? Like, mean area is a number like 1,000. Mean smoothness is a number like 0.1. Well, now I'm comparing these, right? Like, remember what I'm doing back here. This is k nearest neighbors. I'm kind of implicitly, if I'm calculating distance and I'm looking for the closest point, I'm kind of implicitly comparing like these concavity numbers and the radius numbers. Because the radius is now, it's got a huge effect on, well, and in fact, it's not even the biggest one. Mean area, it has this massive effect on how near and far things are from each other. Worst concavity, that's hanging out between apparently 0 and 1.25, that has comparatively no effect whatsoever on what's going on if I'm doing k-nearest neighbors. For Gaussian naive Bayes, each feature is looked at independently, so I kind of expect it will work out. For k-nearest neighbors, I very much don't. And this is like the best visualization I have for this, that if I just look at those two features, if I'm kind of plotting them fairly, everything is inside this box. Mean radius has a scale of 7 to 28, we'll call it, and concavity from 0 to 1.25. So that means like the hugest, like maybe worst concavity is a huge deal when it comes to diagnosing breast cancer. But when I have just jammed it into k-nearest neighbors without thinking about it, well, the hugest swing possible in worst concavity is smaller than even a very modest change in radius. So this feature, because the numbers are bigger, is totally winning when it comes to any distance calculation. You know what, by the way, nobody asked me, and like, I'm always disappointed nobody asks me this. And I think a very good question is, what do you mean by nearest? And of course, you know what I mean by nearest. We all know what distance is, but the fact that it's, well, what is it? The Minkowski metric? It turns out the Minkowski metric with p equals 2, that's distance. That's Euclidean distance as you know and love it. Because we all think we know what distance means, but then we're applying that concept to these crazy numbers that don't make sense to compare in this way. Maybe I'm surprised I get as good, I got 92%. Maybe I'm surprised it's that good, because effectively this feature is getting ignored and this feature is doing all the work. Well, a lot of the work. Mean area. So yeah, like mean area is doing almost everything, right? Like if I just look at the size of these numbers, okay, worst texture, mean perimeter, these things have something to do with it. But yeah, like this might be important and it's just such a small number. that even the absolutely most similar mean area numbers are going to be so much more different than those. All right. Well, of course, one thing I could do here is know something about diagnosing breast cancer. But that's a different course, a radically different course than this one. Maybe what we can do is transform our data and get things kind of into a reasonable range. And, and I mean something like this, like basically have a look at the training data. So in effect, we're training this transformer here. The transformer is going to find the smallest value, map that to 0, basically subtract that number from everything, and then the largest number and divide by the range. So my smallest training point will map to 0, my largest training point will map to 1, and linear in between that. It's a pretty easy calculation. But that means now all of my numbers are between 0 and 1. So at least, like, again, it would be better to know some stuff about the problem domain. But at least now I'm getting all the numbers kind of onto the same range. If I have something where that matters, and it does for k-nearest neighbors, I guess I would expect maybe a little bit better result. Other options here, basically get it so that the mean is 0 and standard deviation is 1. Well, okay, subtract the mean, divide by the standard deviation. That's pretty easy to do. Or understand your data and do something that actually is not crazy. So we can do that. A standard scalar is the mean of 0, standard deviation of 1. Min-max scalar is the 0 to 1 range. I've chosen min-max scalar on this one for no good reason. Again, please don't diagnose breast cancer on my behalf. And I do better, right? So this is better than the sort of dumb k-nearest neighbors, and it's actually better than Gaussian naive Bayes. Cool, right? Is it gonna, well, I guess I can predict, right? And I think the prediction is no. I don't think it will do anything interesting here, just because the thing that happens when I do this make blobs is I get things that are fairly symmetric or have like similar ranges. It's actually one, like I'm giving one standard deviation for all features. And there's like the bounding box of like how big are things allowed to be is fixed, and it's the same kind of across for everything. So I suspect scaling is not going to affect that data to the extent that I'm not even going to bother, but it does affect this breast cancer data set. Just getting everything into the same range. So again, like my visualization here of like the plot for those two features kind of looks like that, where mean radius is just such bigger numbers. If I scale everything from 0 to 1, well, at least everything is in the range of 0 to 1. So a large difference in this is at least a large difference, and a large difference here is equally large. I think that's good. I predict it will let me do better, even if I don't know for sure until I really go and test it. I would expect this to not affect Gaussian naive Bayes, because everything is already considered independently. Anyway, it would just mean slightly different means and standard deviations on the data. Do I want to do the thing, right? I guess if I can figure out what to put in this function call. Oh, yes, I can, because again, this is why this data is not interesting, right? Like, those are the X values. Those are the Y values. And then I can just copy 2 lines of code off the slide. Fine. This is it's fun. It's a good example of, hey, you can do stuff with machine learning. It's not a huge, fascinating thing to put on my resume. Once again, man, talking and coding at the same time. Oh, where's my train? Okay. $93, is that? Yeah, I guess it's, again, randomness in the process. That's similar, sure. So not overfitting, but that's, I guess I'm happy about that. I forget what K I chose on the slides, but it probably doesn't matter too much. But I can do this. Again, I expect okay, fine. I don't feel like it unless I see it right away. No. Okay. Well, I would get that. I would get a similar score. So this helped, like it helped me for K nearest neighbors, and I guess I'm happy about that. I can tell myself a story where that makes sense. I'm happy about that too. Maybe I can do more of this. And effectively, what I did there was kind of like I took the numbers that I got from the world, the universe, like whatever data set I'm looking at, and I kind of I did a little calculation on them in order to create something that makes more sense in the model. And of course, I can do that because I kind of understand what the model's doing, at least for those two, the Gaussian knife Bayes and K nearest neighbors. I have some idea what's going on. So I can make this prediction. I can have this hypothesis that if I scale things, it'll get better because then the numbers are more comparable and the distances make more sense. And I'm allowed to do that. The training data, of course, makes a better or worse model. So I have all these features that I get, like that come from the outside world that are measured or they're in the data set or whatever, but I don't have to just blindly put those into the model. I can do stuff with them and then put them into the model, let them get scaled or whatever. So in fact, we saw this last week or so, which is for the linear regression. We said, okay, but wouldn't it be cool if we not only took some combination of x's and ones, but what we can put in the x squared and x cubed, and then we're effectively doing polynomial regression. Okay, that's great. If I think x squared and x cubed are meaningful and useful, I can put them in there. The thing we just saw was this thing where I say, you know what would actually be better is if things were kind of all scaled into a decent range. And sometimes, like I've seen this work from min-max scalar, if you just have really big numbers, right? If you have huge numbers and you want to do a polynomial fit, well, if you're about to like raise something to the fifth power, maybe you're going to get a numeric overflow and everything's bad. But I can raise 1 to the fifth power. That's cool. I can totally do that. So maybe I want to combine those two. Seems reasonable. Or again, last week I did it for the linear regression because I thought, you know what? I think that this sigmoid thing, I think that's a winner of a value to put into my linear regression because it'll get me a good prediction because I kind of knew something about the data. And well, this is just part of the game. We get to take the observations from the world and we get to transform them in ways that we make sense or that we think make sense. Then we do the machine learning step, or the thing that you sort of think of as machine learning, the model, and maybe that helps, right? So I have this. This is two-dimensional data. I've plotted those two things on the x-axis and the y-axis. But I don't think, well, I mean, I can try it, right? Like I can just YOLO it, throw it into a K-neighbors classifier. I experimented a little bit. 7 worked pretty well. I got a score of 80%. You know, it's kind of an okay number. I guess maybe remember the baseline, right? I have 3 categories here. So just, you know, if I had a model that was just guessed randomly, I would think it would get 1/3 as its score. So I'm doing better than random chance at least. So I can at least console myself and think, hey, you know, maybe I'm not bad at machine learning. But if you have a look at what's going on here, and I suspect if I kind of compared training and validation scores, I'd see it too. The problem is I'm looking at the wrong stuff. Like, it's not like what matters in this data set is not the X and the Y value as they're plotted here. It's the data's in these rings. Like what matters is how far am I from the center of this circle? That's a way more interesting fact, way more useful number to use in my calculations. That if I could throw that into the calculation, I would then predict success. Well, or I guess what I mean by that in the machine learning terminology is if I transform my data to add that feature. Well, here's that. So again, I've got a pipeline with a function transformer. What I'm going to do is take my, well, the things that were plotted as x and y on that visualization, and then calculate the Euclidean distance or the Euclidean norm, or, the x squared plus y squared, and take the square root of it, that thing. I'm going to call that radius. I'm going to think of that as radius. And I'm just going to put those together. So what I'm creating here is now, like, I got my input had 2 columns, and now I have 3 columns in my output. I decided to keep the original x and y values. I like them. And then I'm adding a 3rd column, which is the radius. And I get rewarded for it. It was 80% before, it's 90% now. I am happy. I'm much happier with this model. I don't think I'm overfitting here. I like, once again, like, I'm always surprised just in general, like whenever I make these examples, right, I look at the data and I think I know what example I want to create here, and my fake data is doing the right job or whatever. I'm surprised how much noise I have to add to get the score down from 0.99, right? Like there's huge overlap between these categories. But still, if I do the right thing, I get 90% accuracy. And that's I think a bit of a surprise, but hey, good for us, right? It means you can do okay on problems that aren't too horrible with some reasonable techniques. For this course, I'm trying to remember that machine learning is a data science tool. I know it's not just a data science tool, but in this context, it's a data science tool. And, the thing I'm imagining here is something like this, right? Where it's, okay, I know these things and I want to predict that thing, and I can tell myself a story where that would be useful. And maybe when since I already mentioned it and now I'm thinking about it, I would not be angry if the way you looked at this project was, what sort of thing do I want to have on my resume at the end of this project? If you're interested in health data, then maybe do something like that. If you're interested in, I don't know, I don't want to say anything, because if I say something, you're going to think, oh, that's a good project, he said it in lecture. But if you're interested in problem domain X, like I have a bunch of these examples here, I'm just going to wave at the screen and say, look here, those are some things, right? If you want to have I used a sensor kind of project on your resume, well, then maybe do one. Sorry, I forget, I just add things to this list as they come to my mind. So sometimes it surprises me because I've totally forgotten about them. Anyway, when you're doing this, again, if the problem you come up with has the flavor of, it would be really cool if we could predict, if we didn't have to measure this thing, if we could predict it instead. And then all of a sudden it becomes a target in your data set, and you can see, can I take a machine learning thing and predict it? And then we don't have to measure it because measuring it's really expensive, or you tell yourself some story like that. Okay. The classification problem, or one of the classification problems that you're going to meet in exercise 7, which is soon. Okay, what are we? I'm doing that. So it's next week, the lectureless week. You have data points where there are 3 features, and the features are RGB color values, red, green, and blue. I think I've given them to you as a 0 to 255, like a classic 24-bit color value. Well, maybe those aren't the right number, is the story that we're telling in the exercise, or that I've sort of forced you to tell. RGB color value is just about how to light up a screen to display a color for our weird eyeballs that do this thing. Maybe what makes more sense is to have a look in this other color space where we are promised perceptual uniformity, which is to say, basically, if I take, one step in any direction in this three-dimensional space, the sort of perceived distance between those two colors is the same no matter which way I go. And I don't know what calculation is going on here. That's crazy that they can do that. But the nice International Commission on Illumination has done that, and good on them. Or I have learned in the past to not Google HSV in the middle of lecture. You have to add color space. HSV color space is, well, hue, saturation, and value, or hue, saturation, and illumination, depending which side of this thing you're looking at. But if I gave you these numbers, like hue, which is the x-axis on this little subplot here, this seems really useful, right? If I tell you the hue is kind of in the 120 range, that's green. Everything over there is green. That's probably a really useful feature, I think. I think I can tell that story. It turns out, as with many of these things, this problem is just kind of easy enough that the score changes a little. Like, you definitely do better or worse. It's not as much better or worse as I think I expected when I started looking at it. But what I'm doing here, either way, is I'm turning the data that I got from the world, because the data was originally just about putting colors on a computer screen so they could be displayed to a user and the user could click a button. But if I create more meaningful data, and in this case, it's because I tell myself some story about color spaces, then maybe I can get better results. And I think, spoiler alert, you do. In exercise 8, the problem is, well, it's not weather prediction in the classic sense. It's, here's some weather observations. Like, I'm gonna give you these values, and the category that you're trying to predict is which city. This, a city with this average minimum temperature across January, February, March, and this much precipitation in January, March. That's Vancouverish. That I'm going to predict that's Vancouver. So it turns out I've done a bunch of feature engineering for you, but what I did was, of course, I started with real data, with these 5 measurements that are like kind of reliable. Those are the 5 that are in kind of all of the global GHCN, Global Historical Climatology Network. Every like decent weather station reports all 5 of those. I suspect in some parts of the world, snowfall and snow depth are pretty easy. Just like fill a 0 down that column. But anyway, and 365 days a year or whatever. There's always a few missing here and there. But okay, if I just gave you that raw data and just said, okay, January 1st minimum temperature, January 1st maximum temperature, you end up with that many columns. And that's a lot of features. It's not so much, like lots of processor and memory, like in modern computers are pretty fast. Like if I'd given you this much data, it would not have been a problem. The problem is, though, it's like super wide. There's more columns than there are rows, basically. So how are you supposed to learn, like, what is it about the amount of precipitation on March 17th that looks more or less like Vancouver? It's just, there's so many things that end up having to be trained in a model with that many input features. It's weird and gross. What you actually got, what I handed to you, will hand to you, I guess, is this. I averaged them out. So for each feature, like for the maximum temperature, said, okay, for each month and city, so like all of the Vancouver in this year, January maximum temperatures, average them. Oh, that's the old way to do that. I should update my slide. And then you get a column of each one. Here's the January Tmax. Here's the February Tmax. Here's the January Tmin. So you end up with 60 columns. It's much easier to work with. It also like smooths things out nicely. There's a lot of noise, obviously, in weather. The amount it rains this year on January 3rd at the Vancouver airport is different than last year and the year before that. But if you average across January, then things kind of even out a little bit. So it's just it's just nicer data with less crazy noise in there. And of course, I know that. Like, I know that, you know, the 1st of January and the 14th of January probably have a pretty similar temperature. So it makes sense to average that way. If I'd average like the first day of every month, the second day of every month, that number would be crazy. It's not a meaningful number. I don't expect to make bad predictions on it. Okay. I've done a poor job hitting my lecture break here. Okay, but I will introduce this before we take a break. So I'm gonna, like, I guess where I started talking about Gaussian naive Bayes, and I said, let's think about probability. We'll pretend we're in the probability course. And then K-nearest neighbors is just like, well, pretend we're explaining this to a 5-year-old, what machine learning is, and this is probably, you know, what you'd think of. Decision trees are, what if you're going to explain this to a first-year programmer? You know, this is basically what's going on. I don't know what condition goes here, but like fundamentally, like in this breast cancer data, there's something about a data point in this validation set that's like, well, if the data point looks like this, and if, you know, we've kind of implicitly learned this condition, then return 1, else return 0. If we could just fill this in, we're doing machine learning, right? Well, along with the iris, the flower classification thing, like I said, this is the other classic, everybody uses it as a machine learning, hello world. It's these weirdly low resolution digits. But you know, you're supposed to take these things and return 3 because that looks like a handwritten 3. How big are they? 8 by 8. So there's 64 pixels. Huh. I would have sworn they were bigger than that. But anyway, I've got 64 pixels. Each one of them is a number from 0 to 1 or whatever. It's like how light or dark it is. I'm supposed to take those, and I'm supposed to take this and say, well, it looks like, and so therefore 2. So let's imagine the worst Compute 120 instructor possible. You could make this a class project, right? You could just say like, okay, go for it. Write the if statement, you know, take a 10th of the class, put them in charge of ones, and take another 10th of the class, put them in charge of figuring out what 2 looks like in terms of looking at individual pixels and coming up with an if statement. That sucks. I don't want to write that condition, but I think we imagine it's possible, at least in the theory. So now let's take a break. In the second half today, we'll talk about how it's possible in practice. See you in a bit.